Hi. In this video, we're going to look at three different word problems that can be solved using the concept of work. So let's look at example one. A 20-kilogram suitcase is raised 3 meters above a platform by a conveyor belt. How much work is done on the suitcase? Now, if you recall from the last lecture, there are two definitions for work. Work can be thought of as a change in energy, or work can be thought of as a force times a distance times the cosine of theta. And when I read this first example problem, and I maybe think about the picture that goes along with it, I have a lovely suitcase that is going up this conveyor belt for 3 meters. And I know that the mass of this suitcase is 20 kilograms, but I don't necessarily know. I don't know. I would recommend using the first definition of work to solve this, because knowing the mass and knowing how high I go, it's very easy for me to say that this work must be how much my gravitational energy changes. So this work can be calculated by doing mg delta y. So with my mass being 20 kilograms, my g being 9.8 meters per second squared, and my delta y being 3 meters, I can just plug all of this into my calculator and very quickly come up with 588 joules as the work done on the suitcase. Okay, let's look at example problem number two. Example problem number two says, upon arrival at an airport, a passenger picks up her suitcase and drags it with a 100 Newton force at a 60-degree angle for 20 meters. Oh no, 200 meters. Oops, that's supposed to say 200. From the airport exit to her car. How much work did she do? So she's got her suitcase, right? She's walking and she's kind of pulling on it like this. She must have some kind of, I don't know, rope or something. So we know that if we draw a real quick force diagram, I'm going to do the laziest force diagram you guys have ever seen. Applied force, normal force, probably a friction force in there. Let's see. This applied force is that 100 newtons that they tell us about in the problem. And we know that she's pulling at 60-degree angle. Ooh, this doesn't look like a 60-degree angle at all. I did not draw this to scale at all. But here's the deal. When I think about solving this, I have a ton of forces information here. So I probably would like to use the second definition of work in order to solve this problem. So the second definition of work is to take that force of 100 newtons, take that distance that she walks, that would be 200 meters, take the angle that she's pulling at 60 degrees, right? Because that 60 degrees is going to make it so that only the x component of the force is going to matter. So we love that. And if I put this all into my calculator, then I know that she does 10,000 joules worth of work to drag her suitcase out to her car. All right, let's look at example problem number 3. So Joe tries to push his car up a hill. He pushes it with a force of 300 newtons at an angle of 30 degrees, but the car won't move. So maybe his car stalled or something, I don't know. But here's Joe. He's pushing it. He pushes with a force of 300 newtons at an angle of 30 degrees. There's this force of gravity. Normal force. Excuse me. Here's Joe. He's pushing with that applied force. 300 newtons. But I gotta tell you, the car won't move. So even though I have all this forces information and I say to myself, okay, I can solve this using the second definition of work with all my forces knowledge. Well, it doesn't really matter what that force is because the car won't move. So his D, 0. And so this being 0 really just negates this whole entire thing. He doesn't do any work on it. It's 0. 0 joules of work done by Joe.